This is Physics 2212, Lab 5, Braking with Faraday. So a little introduction. The purpose of this lab was to observe a bar magnet falling down a tube of aluminum foil, and then model that behavior in VPython and compare observational and computational data. So a little preview of the results. The average fall time was 0.345 seconds. The model expected a fall time of 0.3 seconds for the calculated magnetic dipole, and then it expected a magnetic dipole of 3.664 ampere meters squared to match this fall time here. So pretty different, but who knows. The Faraday's law, pretty important to know. So it just relates EMF and the non-Coulombic electric field to the magnetic flux over a closed area, as seen here. And then magnetic flux is equivalent to this equation here. Some other important stuff to know. Magnetic force on a current carrying object can be found by current times change in length across the magnetic field. And then Ohm's law relates current to magnetic flux, where we just take the EMF calculated by the magnetic flux and divided by the resistance of our current carrying object. And then Newton's third law, just that the magnetic force on the loop is equal and opposite to the force by the loop on the bar magnet, so like our individual rings. Our bar magnet here, so that includes our system, and then our surroundings are the aluminum foil tube and earth. So we see force of gravity on the bar. This is the induced current in each individual ring by this bar magnet, and then that results in this magnetic force going upwards on the bar. And we assume that only these two forces are acting on it. So the procedure of this lab was to determine dipole moment, mass of magnet, dimensions of the foil tube, drop the magnet through the foil tube 5 times, average the drop time, and model this using VPython. And now we're going to compare observational and computational results. So our observational results, length of tube, width of tube, all this dimension crap. And then this is what we calculated in lab 3 for our dipole moment. And then the mass of the bar magnet, obviously, and then our average drop time, which was again 0.345 seconds. Oops. So here's our computational model. These are just the initial conditions. So acceleration due to gravity, all this good stuff, dimensions, dipole moment, and obviously our time is going to start at 0. Here is where we calculate the flux because of the falling bar magnet. Pretty cool stuff. And then here's where we calculate the forces by the ring on the bar magnet so that it like slows the fall, which is a lot of math that is work. So here's our model prediction. So this is what our actual calculated dipole moment is based on lab 3, and this is what the velocity over time looks like, and this is what it expected for that. And then for 0.345 seconds, this is the dipole moment the model expected, and this is the velocity over time for that dipole moment. So pretty different. This one's a little more curvy than that. So yeah. So our observational and computational data obviously differ by a lot. So pretty big difference in this shit. And then the results suggest that the lab 3 data was probably inaccurate, which is probably true, and the bar magnet's dipole moment is probably closer to 3.664 than 1.495 ampere meter squared. So some sources of error. Contact between the bar magnet and tube would create frictional force, so it would slow the bar magnet more than normal, and this would increase the observed drop time, which would just increase our observed drop time. Air resistance would again slow the fall of the object and increase the drop time, and then inaccurate measurements and timing would affect consistency of data. So discussion here, if the resistivity of the conductor were reduced to close as possible to 0, the induced current in each ring would be much greater, which means the magnetic force on each ring would be much greater, which means the force back on the bar magnet would also be much greater, and this would increase the drop time of the bar magnet. And then if there were holes or slots cut into the tube, this would affect the ring currents because it would be significantly lower because the hole would, disrupt the flow of current through the ring, so current would be reduced, and because the current's reduced, force is reduced, and force is reduced, which means the drop time of the bar magnet would increase. No, not increase, sorry, decrease. Yeah, it would decrease. So, yep, that's it.